Yes. Actually, at the beginning only we have studied what is my group, what is in my subgroup. So that's a superficial understanding about the group subgroup we did. But in true sense, with the perspectives of the molecular symmetry, while converting from the group to subgroup, how the changes in the symmetry elements or the operation occurs, which operation diminishes, that we are going to study in group subgroup relationships with various example. Let us begin.
It is very interesting to understand the application of group theory to molecular symmetry, to understand the chemicals and their behaviors. If we replace the one of the group by other or one of the atom by the other atom, then we find change in the symmetry. We find change in the order of the point group. That change in the order is possible by deformation of molecule also. Anyhow, if the order of the point group changes, then chances are there those are related to each other. A group which has the low order can relate to the group of the higher order. If we move from the higher order to lower order, that process is called as descent. And from lower order to higher order is called as ascent. So ascent and descent in symmetry, their correlation, which symmetry operations are lost or which are added, that can help chemists to infer structural changes on the basis of observed data or to interpret data more accurately when structural changes have occurred. Now, as is shown in this slide, consider structural changes occurred due to replacement of A by other atoms or group, say B or C. Total 5 structures are in front of you. The structure 1, which is at top, has octahedral symmetry. MA6 is its representation. Total symmetry operations possible for octahedral point group are 48. See the left side structure. Structure number 5. Point group is C3V and total operations possible are 6. What is our definition of subgroup? Subgroup is a group. It is a part of the group. Order of that subgroup can divide order of the main group. See, to number 48, we can divide by number 6. So I can say C3V is a subgroup of octahedral. Similarly, if you see the right side linkage, structure number 2. Point group is D4H. Total operations possible are 16. We can divide number 48 by 16. So we can say D4H is subgroup of octahedral. Let us continue. The structure number 3. C4V is a point group and order of that point group is 8. We can divide by number 8 to 16. Also to number 48. Means what can I say? C4V is a subgroup of D4H as well as of octahedral. Now come to the last structure. That's a structure number 4. That's a C2V point group. Order of that point group is 4. We can divide by number 4 to 8. So C2V is a subgroup of C4V. We can divide by number 4 to 16. So C2V is a subgroup of D4H. We can divide by number 4 to 48. So C2V is a subgroup of octahedral. So it is just a superficial knowledge of the division of any group with the help of order. Now we have to study it in detail. We need to understand which symmetry operations actually are eliminated or diminished because of change in the structure, because of different substitutions. Let us understand the occurrence of structure number 5 from structure number 1. From symmetry operations, you will understand the C3 operation. Number of operations may be decreased, but C3 operation is restored and vertical planes are restored. You may be with the question, where are vertical planes in the structure number 1? Yes, whatever the diagonal planes are there, those diagonal planes becomes the vertical plane. Of course, diagonal planes are one of the vertical plane. In order to distinguish those planes, we are saying it is what diagonal. So though you are finding in structure number 5 vertical plane and in structure number 1 no vertical plane, but understand that diagonal plane in structure number 1 becomes vertical as we decrease the symmetry order. So all operations which are in structure number 5 are part and parcel of structure number 1, and as well as order can divide the order of the main group, means and it is a group. Therefore I can say structure number 5 is a subgroup of structure number 1. Means what I am doing now, I am giving the other insight to understand ascent and descent in the symmetry. Similarly, one more example I give it to you. Compare structure number 1 with structure number 4. In structure number 4, C3 operations are not there, but C2 operations and vertical plane are part and parcel. So in structure number 4, whichever the C2 and vertical planes are there, they are there in other terms in structure number 1. Therefore, structure number 4 is a subgroup of structure number 1. From structure number 4, if I go to structure number 3, in addition to the operations possible in structure number 4, one more class is added. That's a C4 operation class. From structure number 3 to structure number 2, if I move, then there is addition of subsidiary C2 axis, center of inversion, improper axis of rotation, horizontal plane. So because of that addition of symmetry operations, we can say that shifting from structure number 3 to structure number 2 is an ascent in symmetry. And while moving from structure number 2 to structure number 1, you will find addition of C3 operations, S6 operations. So now the concept may be clear to you. While ascending the symmetry, the operations are added, and while descending the symmetry, operations diminishes. Means if I am ascending in a group, ascending in a symmetry, the number of operations may vary, but certainly number of operations of particular class will not be more than the ascending point group. Now let us understand why structure number 5 separately is represented. One simple way I tell to you. Structure number 5, what is the order of that C3 point group? 6. And what is the order of structure number 2? That's a D4H point group? 16. Can we divide number 16 by number 6? No. So order of the D4H is not divisor by order of C3V. Therefore C3V cannot be subgroup of structure number 2. How can we describe or understand that? By means of symmetry operations. See, in structure number 5 C3 operations are there, but in structure number 2 C3 operations are not there. If I am descending the symmetry, then operations cannot be increased, cannot be added, can be decreased. So in C3V point group, C3 operations are added compared to structure number 2. Therefore, structure number 5 cannot be a subgroup of structure number 2. Similar dialogues we can put for relationship between C4V and C3V. In C4V, C3 operations are not there, but they are there in C3V. Therefore, let whatever may be the order, that structure number 5, that's a C3V point group, cannot be subgroup of C4V point group. Similarly, C2V cannot be subgroup of C3V point group, because whatever the C2 operations are there in the C2V point group, they are not there in the C3V point group. So though C3V point group is of higher order, it cannot be ascending in the symmetry to C2V, or C2V cannot be descending to C3V, or C2V cannot be subgroup of C3V. That's the relationship between group and subgroup. With the help of this diagram, attempted to describe the group subgroup relationships. In this example, by substituting A by B or C, we are obtaining group subgroup relationships. We are understanding which operations are destroyed or diminished, whether there is a relationship among them or not. If we are considering any group as ascent, then all the operations in the descending point group should be there in the ascending point. One best example I give it to you, where group subgroup correlation or relationship is not possible. 8. Consider MA5 kind of the complex. This 5 coordinate complex can bear two kinds of geometries. Which are those? One trigonal bipyramidal and other square pyramidal. If I consider MA5 in the trigonal bipyramidal arrangement, then point group will be D3H, order is 12. Keep in mind, D3H, order is 12. But if I represent that MA5 in other possible way, that's a square pyramidal, point group is C4V, order is 8. Formula seems to be the same. We expect that there should be relationship, but there's no relationship because we can't divide number 12 by number 8. C4V cannot be subgroup of 3H. Yes, with this example of MA5, trigonal, bipyramidal and square pyramidal geometries, group, subgroup, relationship, impossibility, clear to you? As a homework question for you is related to your understanding at the beginning, means in 2.2 region. Group, subgroup we have studied. Subgroups for C2V point group, C3V point group, D3H point groups we found out. How many subgroups are there for C2V point group? 4. For C3V, 5. And for D3H, 12. Now I am asking one simple question. C2 is a subgroup of C2V. What you need to do? Just write all operations in C2V, all operations in C2 point group and write answer in a comment box. Which symmetry operations are not there in C2 but are there in C2V point group? Means which symmetries are diminished while descending from C2V to C2. Just write those operations which are diminished in comment box. I like to inform here one more aspect of group subgroup relationships. Higher order point group may remain with multiple dimensional Mulliken's notations. If you remember in Mulliken notations, if 2 dimension then representation was E, if 3 dimension then representation was by T. Such many 2-dimensional and 3-dimensional irreducible representations may possible in higher order point group. Or in other words, as we move down, as we descend in the symmetry, those multi-dimensional irreducible representation will be reduced, will decrease in one-dimensional irreducible representation. Means from higher symmetry to low symmetry, as we descend in a point group, the decrease in the multiple order irreducible representation will be there. For example, octahedral point group, there are two dimensional irreducible representation and 4 3-dimensional irreducible representation. And if I come to structure number 5, that is C3 point group, we can find only one 2-dimensional irreducible representation and there is no 3-dimensional irreducible representation. On the other hand, if I come to the C2V point group, there is no 2-dimensional or no 3-dimensional irreducible representation. All are 1-dimensional irreducible representation. That's the importance of group subgroup relationships.